I'm honored to be here and have the chance to present my recent work. My name is Yanqiu and I'm studying in the College of Mechanical Engineering in Tianjin University. Today, I will give a speech about selection of optimal sensors for fault diagnosis of PEM fuel cell system based on data-driven method. Generally, my speech is divided into 4 parts: research background, method, results and discussion, and conclusion. Here is the first part, research background. As we all know, alternative energy sources have received much attention in the last few decades. Among those alternative energies, hydrogen and fuel cell technology, especially proton exchange membrane fuel cells, has attracted much interest due to its high power density, low operating temperature, and faster response. Nowadays, PEM fuel cells have been applied in many fields such as stationary power stations and automobile industry. However, reliability and durability are still two main obstacles to its commercialization. The typical PEM fuel cell system consists of stack and many subsystems, which makes the fuel cell system a complicated multi-domain knowledge. As a result of this, to accurately detect and identify the faults occurring in the system is not a trivial task. On such basis, a series of studies have been devoted to the PEM fuel cell fault diagnosis. Fault diagnosis, especially online fault diagnosis, has been considered as one of the crucial techniques to ensure the safe operation of the system. To realize online diagnosis, computational efficiency must be considered. On the other hand, when a fault occurs, the abnormal measurements data from system sensors such as current, voltage, pressure, and so on can effectively help us to identify possible fault states. Thus, the use of multiple sensors provides more distinguishable information for specific system faults. However, that leads to a high-dimensional data set during the system operation. Therefore, a sensor pre-selection method is necessary to maintain the balance between computational time and diagnostic accuracy. Now let's turn to the part 2 method. Data preparing is the first step for the data-driven for diagnosis system, and the data are obtained from historical databases generally. Here we can see 20 sensors were placed at the inlet and outlet of the stack, though the specific information of the 20 sensor measurements are displayed in the table 1. As stated earlier, it can be concluded that it is necessary to further investigate the information in the sensors and select sensors that are more sensitive to PEM fuel cell system performance variation. And time frequency domain analysis is a common method in the field of signal processing, which helps to extract the information hidden behind a large number of seemingly messy data. The time frequency characteristic of each sensor in different system states will be calculated using these formulas. It should be mentioned that the Pearson correlation coefficient were also utilized for preliminary screening in previous research. However, the correlation between variables should obey normal distribution and linear relationship. Therefore, the application of Pearson correlation coefficient in the field of fuel cell fault diagnosis need further consideration. Artificial neural network has been widely used in industry fields such as nonlinear control, system analysis, and data classification. As a first-order algorithm, the gradient descent is the most popular method in training neural networks. However, This method is well known for its low training efficiency. Compared with gradient descent processing constant learning rate, the second order algorithm can estimate the learning rate in each direction of the gradient using the Hessian matrix, which can significantly increase the training speed. By combining the gradient descent and the Newton algorithm, the Leeuwenberg-Marquardt is ranked as one of the most efficient training algorithms for pattern recognition. On the left side of the slide is a condition to stop the iteration when using the Leeuwenberg-Marquardt. And the next part is results and discussion. In time domain analysis, the data collected by each sensor is regarded as a whole, and four statistic features are extracted from each sensor. The calculation result can be seen in Figure 3. The larger the value discrimination of the three states at each sensor, the better the response of the sensor to system changes. In other words, the correlation between the sensor and the system state changes increase with the increase of the separation degree of the four features. It can be seen that the four statistic features of the first four sensors are completely coincident in the three different system states, which indicates the sensor is insensitive to system changes. According to the results, the 20 sensors can be divided into three categories as shown on the right side of the slide. In frequency domain analysis, the wavelength packet transform is utilized for the entire dataset. Firstly, the purpose of this process is to find the highest energy, which offers better separation ability for further analysis. You can see from the picture on the left, package 137 are appropriate for discrimination, and the packet 7 corresponding energy value is the highest one. This is consistent with the results in another research. Therefore, packet 7 was chosen. The normalized energy at packet 7 of each sensor is calculated respectively. In the picture on the right, the calculation results of frequency are shown in the figure 4. The score of the sensor labeled as 1, 2, 3, 4, 11, 30, 20, 0 in frequency domain analysis, and the results show a high consistency with time domain analysis. Sensor with a lower score in both time domain and the frequency domain will be removed. Therefore, the anode outlet pressure of stack 1 and 2, cathode outlet pressure of stack 1 and 2, and the cathode inlet temperature of stack 2 and water inlet temperature are filtered. After sensor selection, the remaining variables are selected for training the neural networks. Leeuwenberg-Marquardt skewed conjugate gradient and the resilient propagation, which have been commonly used in supervised learning, are used in the training stage. As shown in figure 6, the Leeuwenberg-Marquardt algorithm has a faster convergence rate, and it has begun to converge in the 50th epochs, while skewed conjugate gradient and resilient propagation has begun to converge in the 150th epochs. Moreover, in the process, the training loss of Leeuwenberg-Marquardt is smaller than another algorithm all along. In conclusion, the Leeuwenberg-Marquardt training algorithm converge quickly with smaller training loss, which has considerable practical value in reality. And to validate the performance of the proposed method, 3 other methods are used for comparison. Table at the bottom of the screen lists the diagnosis performance in the testing data side of the above 4 methods. It can be seen that the proposed method engenders the best results. The high score of the recall rival the proposed method can deduce most of the system faults. At the end of this work, the relationship between the size of the training set and the diagnosis performance are explored. Figure 7 shows the diagnosis results with different training sample size when the proposed methods are applied. The data proportion of the different system states and left is consistent all the time, where in the right one, only the data of healthy and unknown are added in the training set. It can be seen that the accuracy diminishes with the decreasing training sample in the right. This rivals that the proposed method is suitable for dealing with large-scale training set. However, the record score doesn't appear the same training as the accuracy. The lowest recall is obtained when all data sets are utilized. Well, in left finger, the recall and the accuracy show consistent change. They increase slightly with the increase of sample size. Therefore, we speculate the change of diagnostic performance should be caused by data imbalance. So, except for collecting enough training samples for better diagnosis results, the data balance also should be noticed in the practical data accumulation. Nevertheless, in practice, the amount of data collected in the fault condition is far less than the data in the healthy. To solve the imbalance problem thoroughly, in the next work, the method of modification to the weights of data under different stage states in the loss function of the classification model will be adopted. In conclusion, the overall results indicate that the optimal sensors can yield reliable system information and reduce unnecessary calculation burden. The Leavenworth-Marquardt-based method offers the possibility of online diagnosis because of its high computational efficiency. It should be mentioned that the proposed method in this work is an end-to-end learning method. That is, it only requires using the original system variable to predict the system of the system directly, thereby reducing the reliance on the physical model of the actual PEM fuel cell system. The above work are all I want to share. Thank you for your listening.